All right. So I posted an announcement on Canvas. I'm not positive announcements are enabled, but hopefully if you look on Canvas, you'll see an announcement. If not, I'll figure out a different way. But there's a link to a YouTube channel, a playlist that will be where I post our videos. There we go. So it's still uploading and processing, but they should be posted up there. All right, so some people who weren't able to get into CTEC before have been able to since then. You got in? Okay. So if you were getting connection reset by peer and so on, I think it was just a transient issue. But it's still not letting me in last time I tried.
It had just a brief window. It backed out for me.
Okay, cool. All right. Let's talk about programming. So this is a programming course. We talk about programming, we hear about programming, we talk about being programmers, and so on and so forth. I'm going to tell you something that may sound startling. The real gist of computer science is not so much programming per se. I actually think of it as more a question of communication. Communication in the sense that we have these computers that are willing to do whatever we tell them to do. The challenge is figuring out how to tell them what we want. And there's two aspects to this challenge. The first aspect is not too bad. The second aspect is where we're going to spend most of our energy. So we need to be able to tell the computer what we want it to do. I want you to ask me how many energy drinks I'm buying and how many bags of potato chips I'm buying, and then I want you to figure out the total cost for all of that. And I want you to calculate the tax, because some of these are taxable and some of them aren't. And then I want you to tell me the total amount of money that I owe. That's what I want my computer to do, because I'm selling energy drinks and potato chips in the parking lot all summer. And today we can't tell a computer a description like what I just said and have it actually go off and do anything reasonable. Okay? So the first challenge is we need to learn the language that the computer understands. And at the lowest level, the computer understands a very, very odd language. It understands a bunch of ones and zeros. If you look in the memory of a computer where all of its instructions are stored, you just see 1100, 11110010 for 16 billion times, depending on how much memory you have. That's what the computer understands. It doesn't understand add these two numbers together. It understands 11100101. And at one time, that's how you had to talk to a computer, right? Literally, it was 1101, right? But that doesn't work very well, so people started coming up with languages that you could use to describe what you want a computer to do, and ways to translate from those higher level languages into the ones and zeros. And these higher level languages started off pretty low level. If you take Engineering 270, we work in assembly language. That's a very low level language. It's not a whole lot better than the ones and zeros, but it actually is. But it's at the same level. It's these cryptic looking things that don't make any sense to most people, but if you know the language, you understand what it means, and you can change what you ask the computer to do by specifying things in this weird language. High-level languages like C or Java or Python or BASIC or Fortran or COBOL or any of these languages that you've heard about are designed so that we don't have to work too hard to go from the language that we work in and that we think in to describing what we want the computer to do. So the language issue is not really the big deal, because we have tools that will convert from a pretty comfortable language to the ones and zeros. The bigger challenge is this. What the computer can do is very, very limited. Okay, computers can add numbers. Most computers can multiply numbers. They can compare two numbers. Okay? Most computers, if you just look at the hardware, cannot let you type on a keyboard and use that to create a document. They cannot go to a site and pull down a web page and display it to you. They cannot move a spaceship around and let it fire missiles when you hit the space bar and hit little floating rocks. Okay? These things are way beyond what a computer can do. What we have to learn to do is take what we want the computer to do and break it down into little tiny steps. The small steps that the computer is actually capable of. And some computers, the set of things that they can do is, 20 or 30 things. That's it. And everything that we ask the computer to do, I want you to let me type an amount of time for my microwave oven to run by hitting these numbers on my keypad. And I want you to beep each time I do that and display my time in green. And then when I say start, I want you to start counting down once per second, and I want you to drive the microwave generator until you get to 0, etc., right? You have to take that and break it down into these 20 or 30 things that the computer actually knows how to do. And that's what the art of programming is. It's really translating your goals into these little tiny steps. And that collection of little steps that you want to have performed, that's what we call the algorithm. Okay, so the algorithm is how we translate what we want to have happen into something that the computer can actually manage. And that's really the bulk of programming. Once you know how to break your task into these small pieces, it doesn't really matter if you're working in assembly language or Python or Java or C or any other language, right? That's just taking this thing and putting it into some other language. And we're really good at doing that, right? We're wired to be able to work with different languages like that. It's really about algorithm development. And we'll start seeing that next week when we look at Program 2. We'll start thinking about algorithms, how we can take it's the shopping problem where we're buying energy drinks and potato chips and such and trying to figure out how much it costs. We'll start breaking that down into little steps and see how we can get it into pieces that C can handle. Does that make sense? Somewhat? Okay. So, since the CTEC server doesn't seem to want to let me log in, I'm just going to pretend that I'm sitting on the CTEC server right now, even though I'm just sitting on my own Linux machine. But once you log into CTEC, you get a window that looks like this. There's a prompt that usually says something like CTEC dash, and it's got your username and maybe some other information. And then there's something like a blinking cursor. Okay? Blinking cursor basically says, I'm waiting for you to do something. Okay? And if I start typing on my keyboard, right, whatever I type appears right here and it echoes it back to me. Right? Putty SSH is not, when I hit the letter A, it's not putty or SSH that's displaying a letter A. When I hit the letter A, that gets sent to the server, and the server generates a letter A on its output. And if that comes back, if this is putty, it sees that the server generated the letter A, and it'll go ahead and display the letter A. So every time you type something here, it's going across to the AA cluster. The letter's coming back. That's what you're actually seeing here. Okay, so CTEC is a computer that you're running remotely through putty or SSH, and it's a Linux system. Okay, most systems in the world are Linux systems today. And any computer has some sort of operating system, right? Some set of code that's running. If you're running a Windows machine, right, there's code running which says when I move my mouse this way and I click here, I want you to open a browser, right, or whatever. So this is similar. This is an operating system. It's called Linux, but it was developed before mice were a thing, and before graphics was even a thing. So Linux is fundamentally a command line oriented language. It means that it's, how many people here remember DOS? Right? It's kind of like DOS, right? Windows is sort of like DOS with point and click added on top of it. take away the point and click and just go back to the stuff underneath. That's what we've got here. And that can seem really crude in some ways, but it's actually really, really powerful. Because if you have a point and click operating system, you can only do the things that the people who wrote the operating system decided to let you do, which are pretty limited actually. From a command line, I can do pretty much anything I want. And this is why, you know, for so many years, even when Windows was the operating system, people kept dropping into DOS. Because there were things that you could only do from DOS, like change the permission on every file from this folder on down. There was a time when you had to go into DOS to do that and use one of these cryptic commands. All right, so you have a handout called Basic Unix Commands. Unix and Linux, same thing. Okay, Unix was developed by Bell Labs decades ago. Linux is an open source version of Unix. Unix was not free when it was developed. It was very expensive and it was completely closed source. It was something like $40,000 to look at the source code. Linux is an open version of it, so you can own it, you can put it on your machine, you can modify it. So interchangeable for the most part when we say Unix or Linux. So basic Unix commands. And let me cheat. Pretend I didn't just do anything. Okay. If you're on the CTEX server, right, you can more or less play around with these things at will. The system should be set up so that you can't accidentally delete someone else's files or system files or do something that like causes harm to the server. Now that doesn't mean you should take that as a challenge and try to find a way to crash the CTEX server, because you can do that. Okay, but it gets people really unhappy and it always leaves footprints and it can cost you your account. But you know, playing around with these things to see what these do, pretty safe, right? But if you've just spent a week writing one of your programming assignments, that's not the time to start experimenting with, I wonder what this command does, okay? But early on, right, if you don't have anything to lose, feel free to experiment. And this is another thing that I always try to tell my students. The best possible way to learn some of this stuff is hands-on, right? You can read it, you can go watch an entire video on what the ls command does. You can look at the documentation for ls, and it's, you know, 50 pages long, and you can read that from beginning to end. That's not going to tell you as much as just typing in ls, typing in ls-l and just playing around with it, seeing what happens. All right. And you can get by without really understanding a lot of this, but don't. It's really worthwhile having a good feeling what you're doing when you're working on the CTEX server or whatever system you're on. The more comfortable you are, the more familiar you are with this environment, the more successful you're going to be in your programming courses. So let's just play with some of these things. So let me start fresh. So ls shows you a list of files in your directory. These are some of the files that I have sitting in my current directory. And you know, everything scrolls off the bottom of the screen, so if you've got a bunch of stuff, you're missing the top of it. But if you've got a mouse with a scroll wheel, or if you're good at using scrolling on your touchpad, that helps a lot. So, so those are some of the files in my directory. Most commands have the option of specifying what's called a switch, one or more switches, the modifiers on the command. So ls is the command which says, show me a listing of the files in my directory. If I say ls-l, that says, yeah, do the ls command, but modify the behavior. -l says, do a long listing. And so if I say ls-l, I get one file per line, and I get all this extra information on there. For example, it's telling me that this file down here is this many bytes. Okay, that's a video, so it's hundreds of megabytes. The date and time that it was modified, the owner, that's me, Nick, The permissions, so I don't think we go through permissions in this course, but you will in 224. But basically, who has access to read and write and execute these files, and so on. These things with a D in the front say that this is actually a directory. It's like a folder that has other things inside it. These things are called links. It says when I say pop, it actually refers to a totally different folder, which is all of this stuff. But I don't want to specify all of this every time that I want to move into this folder, so I just set up a shortcut. And pop is a shortcut to that. If I say ls directory name, it'll show the contents of what's in that directory. So if I want to see what's in the pop directory, I could say ls pop, and that's what's inside there. Bless you. I had a directory called CSE 121. It doesn't have anything in it. There's another option, ls-a, which says show me everything in the directory. And ls does not show you everything that's in directory. If I say ls-a, I see there's actually two things in here, dot and dot dot. Those are kind of mysterious. Let me go back to my original directory. If I say ls-a, I see all these new files here, things that start with a period. These are called hidden files. Usually you don't have to worry about these. They're files just like any other file, but ls was written so that if a file begins with a period, ls won't show it to you. But ls-a will. Why do you want to do that? Because there's a lot of these dot files, and usually you don't care about them. And if every time that I do an ls, I'm looking at 80 of these special files, it gets in the way of seeing what I actually want to see. So it's just a convention that when you say ls, things that start with a dot, they're called hidden files. Hidden files aren't shown. If you need to see them for some reason, you can say ls-a. All right, copy copies one file to another. Most commands, the output file is the last thing, not always. But usually, if there's an output file, it's the last one in the command. But you can always come back here and see what the order is. So copy file 1, file 2 will copy from file 1 to file 2. So if I do an ls, I've got an xinfo.txt. I can copy xinfo.txt to zzz and now I've got a file called zzz and it's a copy of xinfo.txt. If I say rm, that'll get rid of a file. So I can say rm zzz and now that file's gone. So all the things that you're used to doing possibly on other systems, there's ways to do from here also, but it's usually done by typing commands. All right, let's talk a little about directories, because this will be useful to you. So PWD shows you what folder or directory you're currently sitting in. I'm on my own Linux system, so my directory is /home/nic. If you do this on the CTEC server, your directory will be something like /home/students/ your username. So first initial dot last name. Wonder if I can get in yet. Hey. But I forgot my password. So. Oh. Okay. So if I do pwd, I'm under /home/faculty/username. If you're a student, it's home student's username. So this is a folder. Okay, this is where you end up when you log in. You can create new folders. Okay, just like you do on a Windows system. The command is makedir, mkdir, and then the name of the folder that you want to make. You can put spaces in these things, but don't. Okay, it makes things confusing. Stick to things without spaces. Unix is case sensitive. Okay, so if I say pwd uppercase, it has no idea what I'm talking about. Okay, so case is important. So I can say makedir CSE 121. And now if I do an ls, I've got a directory called CSE 121. And if you want to move into a directory, you can say cd in the name of the directory. So right now, I'm in my home directory, right, home faculty and Macias, and I've got something called old and something called CSE 121. If I say change directory to CSE 121, now it tells me I'm in nmacias/CSE 121, and there's nothing in here. Right, so it's just a different folder. So if I want to work on project 1, I could say makedir PA1 and then cd into PA1, and I can do all my work in this directory. And later on, when I start working on PA2, I can makedir PA2, and now I've got two separate directories for my two projects. So you can save your code from other programs, right? And you can break things off into different pieces, and if PA2 is not working and I want to try a different idea, right? I could make, you know, PA2.2 and do some work in there. And this is one of these things I was mentioning before about organizing your environment, right? Finishing CSE 121 with 500 files in one directory with names that hopefully remind you what they are is probably not the best strategy, right? Take advantage of the fact that you can put things into different directories and split them up accordingly. So that's a bit with directories. So makedir and then cd moves into a directory. And if you want to move up one directory, you can say cd ... and that brings you back up. So I'm in CSE 121. If I cd ... that puts me back to my home directory. If I cd ... again, that's going to put me under /home/faculty. And now I can see the names of all the people who have faculty accounts. Can't do anything with it. If I try to list Scott's directory, it tells me permission denied. And if you just cd, that brings you to your own home directory. All right, other commands that are useful to know. Cat will show you the contents of a file. So I'll come off my server. So if I want to see what's in xinfo.txt, hopefully this isn't anything bad, like passwords. So that's the contents of that file. And it's pretty long. I'm sure it was meaningful to me at one time. So there's a command called less, which is kind of like cat, but it shows you the contents of a file one page at a time. So if I say less xinfo.txt, it shows me the first page of my file, and then I can hit a space bar and see the second page, and I can sort of go through it one page at a time. And then when I get to the end, it tells me end. And then if you hit the letter Q, that'll quit your program. And now you're back to a prompt. MV lets you rename a file. So you can do the same thing basically by copying a file and then deleting the old file. But you can use MV that actually renames a file in place. And so move original file to the new file. All right. One of the nice things about Unix is it comes with built-in manual pages. So all of these commands that we're looking at, you can find documentation for that on the system itself. So for example, if I want to know about the less page, I can say man for manual page and the name of the command less, and it will tell me all about this command. So it gives me a one-sentence description opposite of more. Well, that doesn't tell me much. Different ways that I can use it, different switches that I can put on the command, and then a description of what the program does. and then commands that I can use when I'm inside, and so on and so forth. And again, this is like, you know, tons of documentation on this one command. Don't sit down and read this unless you're really interested in it, right? Because this is just lots of stuff. 1,553 lines of documentation. And I can look at the more program, and it'll tell me it's file perusal for CRT viewing, right? And if I want to know about the man command, I can say man, and it'll tell me about the command called man, right? So everything is documented on here. And it's useful for kind of a quick reminder of some of this stuff. When you're programming, you're going to be using functions in C to do things like print, for example. There's a command called printf. And if you say man printf, right, that'll tell you information about the print function. And this is a virtual manual, but you can picture it as having 8 sections. Section 1 are basically UNIX commands. Section 3 are basically functions you would use from, say, a C program. Those are the 2 main sections we're interested in. This little 1 in parentheses means that this printf is actually a UNIX command that it's describing. If I want to see how to use printf as a function from a C program, I could say man3 printf, which says show me the version from chapter 3 of the manual page. This is the thing that I can actually call. Right, this is something that we'll start to work with a little bit today, but we'll get into in a lot more detail later. So online documentation, which is useful, right? And this is on the machine itself. So if you put Linux on your own machine, you don't even need a network connection, right? It's sitting right there in your hardware. All right, Control C. If you have a program running and it's supposed to do something and then stop, and it doesn't stop, it just keeps running over and over and over again, right? Don't panic. You can always kill your programs. And the way you kill it, hold down the Control button and press the letter C. That generates an interrupt and it should stop your program. All right, and the last 2 commands on here are the ones you're going to use the most. So GCC calls what we call the compiler. And here's the picture to think about. Remember, we have to tell the computer what we want it to do. Right? And this means we have to specify a sequence of instructions in a language that can be translated. Okay? So we're going to write files, kind of like if we were writing documents, right, or writing a book or something like that. We're going to create files on the CTEX server, and these files are going to contain a description of what we want the computer to do. Okay? Those files are usually just called source files. Source as in containing the source code, the code that we've created. And they're usually files called something.c. And in Unix, right, you can have files that look like temp or test or steam, or you can have files like xinfo.txt, where this period specifies an extension. So clarkreg2.mp4, that's a video file. Okay? And if I have something that ends with a .c, that's usually a C file. All right, so we're going to create these source files, pa1.c. And now that has to get translated into something that the computer understands. And so there's a compiler. And the name of the compiler we're using is just GCC. It's a program. But by running GCC, the computer will take this source file and translate it into an executable. An executable file called a.out. And once you have an executable file, you can say ./a.out and actually execute it. All right, questions so far on this? This is like the 40,000 foot view of all of this. We're going to drill down into the details as we continue. But this is just kind of a high level pass over these ideas. Okay, so let's talk a bit about C. So why do we care about C? A lot of schools, a lot of programs are going away from C. Some schools teach Python, and they use that as the first programming language. A lot of places use C++, which is a more modern, more powerful version of C. We use C, and it's come up a few times, and I've always lobbied pretty hard to say we should be teaching C in these courses. So why do we care about C? C was in some ways designed to basically be very close to the level that the computer actually understands. And there's reasons why it's nice to work in the language that the computer understands, because every time you go to a higher level and you have some program translate from that to the machine code, you lose things like efficiency, right? If you write directly in machine code, you have complete control over what the computer is going to do, right? And in some way, that's really powerful. But it's very difficult to do, right? Writing ones and zeros or even assembly language is very painstaking. So C was developed in some ways to let you write in a more comfortable way, but not be too far removed from what's actually going on in the hardware. So as a result of that, partially, C is extremely efficient. Okay, your code runs very efficiently, and it doesn't take a whole lot of space. The programs that you write here, once you compile them, if you look at the size of the executable, it's going to be thousands of bytes. If you look at most executable programs that you download, they're millions or hundreds of millions or billions of bytes, right? So C is fairly lean, very compact code. It's also very portable. The language has been around since the 70s. It's been standardized through several different levels. And if you write C code well on one machine, you can take the source code to another machine, recompile it there, and re-execute it. And so it's highly portable. It gives you access to the hardware in a lot of ways. Okay, that's that idea of keeping close to the assembly language level. It's similar to a lot of other languages. C++ was a variant of C. Java is very C-like, right? Objective-C, C#, JavaScript, right? All these things use the same kinds of constructs that you find in C. So once you've learned C and you've gotten good at taking what you want the computer to do and breaking it down into C-sized steps, it's pretty easy to move over to some of these other languages. And the language is going to look very familiar to you. The way that you write an if statement or a while loop or an assignment statement, it's going to be almost verbatim in a lot of these other languages. The last one here, this is the main reason that I advocate for C. It really helps you understand what's going on inside the computer. You have to understand what's going on inside the computer. Python, you can just write Python code and have no idea what's actually happening, and it works great, right? C, to actually make some of the things that we want to do, especially in the 200 level courses, to actually make those things work in C, you have to be able to think about what's going on in the hardware. How is memory organized? What's the CPU doing at this point? And that's useful for learning, right? Once you get through that, you understand the whole spectrum from hardware all the way down to software. And that's just really powerful for a computer scientist. C is used everywhere, right? It's common for at least the lowest level part of a lot of operating systems, but entire operating systems are written in C. What is Linux written in? C, right? What's the C compiler written in? C, right? Everything is done in C. What's Java written in? C. Right? So it's kind of ubiquitous. It's also really good for embedded systems, right? The controller inside your refrigerator that monitors the temperature and shows the time on the front and all this kind of stuff. There's a good chance that was written in C. And if you've got a little microcomputer sitting inside your refrigerator, right, you probably can't put a few gigabytes worth of code on that processor, right? It's a small little thing. It can probably handle, you know, a few thousand bytes maybe of code. If you write something in C, it'll probably fit. Certainly better than writing in something higher level. MATLAB's written in C. Web browsers are written in C. So it's a really common, well-used language. It's probably not going away anytime soon. And like I say, it's a really good building block. It's a place to start from and segue into other languages. So it was invented in '72. The C programming language, if you can find a copy of this book, get it. It's a collector's item. Kernighan and Ritchie were the two people who sort of developed the language, and they published this C programming language. That was the way that you learned C in the day, and it's everything that you need to know about the language and about that much. So that was 1978. 1989, C was updated to support ANSI C, so American National Standard something. So it's a more standardized version of the language. And then 10 years later, C99 came out, and then about 10 years later, C11 came out. So roughly every 10 years, updating the language to take into account how computers have changed, right? Computers are more parallel. We have machines with multiple cores and so on, and so some of that was added to the newer versions of the language. It's a small language. So C89, which is not the original version, has 32 keywords, right? This is basically your vocabulary for talking to the computer through the language of C. I've been programming in C for close to 40 years, and I've probably used like half of these. Some of these I've never used, right? So it's a really simple language in a lot of ways. And the trick slash fun slash challenge of programming is I want to do all this crazy stuff with my computer, but this is all I have to talk to the computer about. So how do I break down my task into these small steps, right? Assembly language gets even more extreme. And I like to use the example sometimes of cooking, right? So anybody here like cooking? I like cooking. I don't do it, but I like it. There's a creative aspect to cooking, right? Which is what spices am I going to add in here, and how much should I reduce this sauce, and what can I do to adjust this, and so on, right? That's the creative part. And then there's kind of the drudgery part, which is I need to chop 5 onions, you know, and I need to peel 13 cloves of garlic, and I have to wash the dishes afterwards, right? And so you get a sous chef to help you with this, right? And you can say chop 5 onions, you know, in such and such a way, and the chef will do that, and now you've got your onions for you, and you can deal with the creative part, right? So a computer is kind of like the ultimate assistant. It will do anything you ask it to. It will do it quickly, it will do it perfectly, it will not complain, but it only understands a few things. So you've got an assistant in the kitchen and you say chop that onion, and they're just going to stare at you and say, what's an onion? Right? So imagine trying to break it down into the smallest steps possible. Get a knife. Well, how do you get a knife? Well, you have to open the drawer. Well, how do you open a drawer? Well, you have to put your arm on the knob. Well, how do I do that? Well, you know, extend your shoulder and tilt your elbow down and walk forward. Well, how do you walk forward? So you got to tell it how to walk. And get over here and then close your fingers and now apply this much force backwards, right? And now you're looking at the silverware, right? And continue like that. So imagine trying to break things down into these tiny little steps. If you can do it, this assistant will do exactly what you want. And it'll do it, you know, billions of times a second. But the challenge is getting it into this simple language. So this was C89, 32 keywords. 10 years later, they added a few more keywords. for different types of numbers, complex numbers, and so on. C11, they added some things for threading, for running multiple versions of your code, and so on, but still a pretty small language. All right. So we say C is a typed language, and old computers really only worked with one type of thing, which was an integer. And integers were these really small things. They went between roughly 0 and 250. So they were very small integers. And everything you wanted a computer to do, you had to build up out of these little tiny numbers. And if you wanted to find the area of a circle, right, pi r squared, there's no way to do that directly because pi is not an integer. You could pretend it's 3, right? And your radius is 4.5, maybe you just call that 4, and you could say 3 times 4 squared, and say, oh, the area is 48, right? But if you actually want to do things with real numbers like pi or 4.5, you have to sort of figure out how to do that. Modern hardware understands both integers and real numbers. Okay, processor inside our laptops understands real numbers. The processor we use in Engineering 270, the PIC processor, does not understand real numbers. It understands integers. The small ones from 0 to about 250. But most languages, most computers understand integers and real numbers. So let's talk about variables, and then we'll segue into types. A lot of what we're going to do with computers involves arithmetic, right? Adding things together, or comparing two things, or subtracting or multiplying. That's a lot of what we're going to do, even if we're not writing a program that's purely about math. You know, if you're playing a game, you need to keep score, and so when somebody wins, you need to add 1 to the number of times that they won. So you can say this person won 7 times, this person won 5 times. So we do a lot of things with arithmetic. So there's a concept of a variable. And a variable is like a box. It's a box that can hold something. And for now, we can just think of it as holding numbers. Okay, whole numbers, integers. And we have to give these boxes a name, so I might call this box X, and I might call this box Y. And we'll see that some of these keywords are used to specify that I want a box named X that holds an integer. That's the keyword int. So if I say int space X semicolon in my program, when I compile this program, right, this is a file that I'm writing. It's got a line in it that says int X semicolon. When I compile that, when I run it through GCC, the program GCC, the compiler, will look at that and say, oh, Nick wants a box named X that can hold an integer. And it will do something so that in this executable program, when I run this, when I say ./a.out, the operating system will set aside a space in memory that refers to this box named X that holds an integer. And if I say something like X equals 12, when that gets compiled, a.out will have code in it so that when it's executing, it will cause the computer to take some way of representing the number 12 and put that inside this box named X. And then if I say something like Y equals 2 times X, that will compile into code so that when it executes, the computer will say, okay, let me look in this box named X and see what value's in there. Oh, it's got the value 12. Okay, star means multiply. Take 2 and multiply that by 12. That's 24. And this says, take the value over here, 24, and put that in the box named X. And the CPU will magically cause a 24 to appear in here. Okay, that's the level of thing that's going to be happening. So one of the tricks is that certain boxes are only good for certain types of things. If I say integer x, I can store a 12, I can store a 20, I can store a -5, I can store a 0. In fact, I can store any number between plus and minus 2 billion, as long as it's a whole number. But I can't store the number 0.5. If I want to store a real number like that, I can't say int x, I have to say something different, like float x or double x. Or maybe I want to store a character. Maybe I want to store the letter J. And so I could say character space X, and now X is a box that can hold a letter. But each type of box has a particular type of thing that it can hold. Okay, so these are variables, X and Y, for example. They have a certain type. Okay, so this is what we mean by data types. What type of thing are you putting inside a box? So data types are the things the computer works with, the types of information. And barebones C understands only a few types. So characters are used for a single letter. Integers are used for whole numbers. Booleans are used to store just a 1 or a 0. I've never actually used a Boolean in a C program in my life. Doesn't mean you shouldn't, but a lot of times we use integers to represent true or false. And then floats and doubles, these are two types of real numbers. And floats aren't as wide in range or precision as doubles. And generally we just use doubles. I've never used floats in a program either, most people don't. So the main ones to worry about are integers and doubles and somewhat characters, and then eventually bools. All right, so there's some sample code. Integer age says age is a variable of type integer. Age equals 37, sets it equal to the value of 37. This third statement's a bit mysterious looking. Age equals age plus 20. If you were a mathematician, that would just kind of blow your brain. Because how could age be equal to age plus 20? That's never true, right? Age is equal to age. Age plus 20 is something different. So this is something that we can actually think of a little differently. Think of this arrow, think of this equal sign as kind of an arrow. When you say something equals something else, it's really saying calculate the value of something else and then copy that into this something. So this means take the current value of age, add 20 to it, and now change the value of age to be that. Does that make sense?
So it would already have a reference to what the age was.
So presumably somewhere you said something like age equals 40. And so now it says take 40, add 20, that's 60. Okay, set age equal to 60. And now it's no longer 40, it's equal to 60. So I know someone who used to call that equal sign a goes into. Like age plus 20, it goes into age. So you think of it as an arrow pointing to the left. All right, so where are these things actually stored? What do variables actually look like to the computer? You know your computer has memory, right? You used to have to upgrade it a lot. Now mostly I think people just get new computers. But desktop systems in particular, you'd go out and you buy this little stick of memory, right? And you pull the cover off and you put that inside. And you get that memory, it says something like, 2 gigabytes of memory, or 8 gigabytes, or 500 megabytes. It's always something bytes, right? So what is a byte? A byte is the fundamental unit of storage inside a computer. And a byte is composed of 8 what we call bits. Okay, a bit is just a 1 or a 0. It's a binary digit, B-I-T. Decimal, humans, 10 fingers, we came up with 10 digits, 0 through 9. Okay, computers, much simpler, 2 digits, 0 and 1. Okay, so these binary digits are called bits. If you take 8 bits together, that creates a byte. Okay, if you take half a byte, that's called a nibble, spelled with a Y. So 8 bits, 1 byte, that's sort of the fundamental building block. And if you have a character is actually stored as a byte of memory. It takes the 8 bits and it codes your character using some peculiar coding. For example, if you have the letter A, that will get coded like that pattern of 8 bits. There's no inherent reason why that's the letter A, it's just agreed upon. It's actually something called ASCII. And you talk about this a little in CSE 120, I think. Engineering 120. So if I say initial is a character and I said initial equal to S, there's some pattern of 1s and 0s being stored in this box that's called initial. And it's the pattern that's been agreed upon as representing the letter S. All right, double temp F, temp C, so I'm declaring 2 boxes for holding doubles, these real numbers, one called temperature F, the other temperature C, and this is trying to convert from Fahrenheit to Celsius. So if we set temperature F equal to 98.6, what's the rule for converting from Fahrenheit to Celsius? Subtract 32, divide by 1.8. That's just the rule. And so this line of code says take temperature F, subtract 32, I've got parentheses around that, same parentheses you see in algebra. Take that new quantity, the difference of temp F and 32, and divide by 1.8 using the slash for division. That thing on the right of the equal sign is now the equivalent temperature in centigrade, and this statement says take that value and assign it to temp C. So after executing this line of code, temp C is now the centigrade equivalent of 98.6 Fahrenheit. All right, so what can we call our variables? More or less anything we want with just a few restrictions. Again, things are case sensitive. So uppercase temp is different from lowercase temp. Temp with a big F is different from temp with a lowercase f. So case matters. And there's a few rules. We have to begin with a letter. Okay, we can't begin with a number sign, with a number like 8. Technically, you can begin with an underscore, but it's bad practice to do this. Okay, the reason being that underscores are usually used for special variables. So we try not to use underscores in the beginning of our variables. You can use them after the beginning, but not in the very first spot. Can't begin with a number. You can't begin with a strange symbol like a pound sign or a quotation mark. You can't include things like dashes or slashes. Why not? What would be wrong with having a variable named this?
Directory.
Could be. What else?
It's dividing by hot.
It's dividing, right? If I say temperature equals temp F slash hot, how does it know if this is a variable or if this is 2 variables that I'm asking it to divide? Right? It's ambiguous. So most of these rules are to make it possible for the compiler to do its job without ambiguity. So we start with a letter, and then we can have any combination of letters or numbers or underscores, uppercase or lowercase, pretty much whatever you choose. And it's good practice to use descriptive variable names, right? Over here when I said x equals 12, y equals 2 times x. What is x? I don't know. Now if I said something like price equals 12, new price equals 2 times price, right? Well, now I've got some idea what these variables are doing, right? And since you have the flexibility in C to use pretty much anything you want for a variable name, there's nothing wrong with being descriptive. And it'll actually help you a lot with your coding. Let me mention something else in here. So earlier languages like Fortran, for example, you couldn't name variables age or tempf or things like that. Your variables were a single letter or a single letter followed by a number. So you could have I, or you could have J17, or you could have X11, but there was no way to have a variable named something like time, T-I-M-E, right? So as languages started to become a little more user-friendly and we could have actual words for variable names, a couple of ways of taking advantage of that developed. One way is called snake case. And snake case was using underscores to break up a long string of letters into words. Now we can't use a space in a variable name because that won't be understood by the compiler. But if I wanted to represent the current time, I could say something like current underscore time. And that's pretty unambiguous what that means. That's the current time, right? Whatever that is in my program. And it's easier to read than just everything slammed together, especially if your description involves multiple words, right? So time at beginning of cycle, right? You put underscores. That's snake case. That gave way to something called camel case. And camel case, the idea is you uppercase the first letter of each word, except the very first letter for some reason. That's just the convention. So I could represent current time as something like current and then time, all right, for this cycle. And you'll see those terms tossed around, camel case and snake case. That's just what it's referring to. And depending on where you work and who you work for, right, your whole coding style may be governed by a set of rules, right? So some schools have a style guide. It can be 30 or 40 pages long that say what your variable should be called and should you use camel case or snake case and how much should you indent your code and all this kind of stuff. And to me, I don't care as long as it makes sense. But you know, do something that's reasonable for you. Do something that's descriptive, but not too long to be unuseful. All right, so primitive types in C. So we mentioned character, integer, bool, float, double. There's also something called a void. Not a void. And void is not really a data type. It's really used when we want something that doesn't have a data type. And that's not going to make sense until we talk about functions, which is later in the course. And then there's pointer types, which is a data type followed by a star, and that's going to be way towards the end of the course. So we won't encounter those too soon. All right, we've talked about defining variables. I can define 3 variables on one line. I could say integer sum semicolon, integer total semicolon, integer interest rate semicolon, or I can do it all on one line, just integer, and list all the integer variables that I'm declaring. Either way. These are kind of just nuances of the language, and they're things that you'll pick up and you'll find a style that you prefer and sort of run with that. All right, we talked about the assignment statement, right? This is not an equality. This is saying calculate the value on the right, assign it to the variable on the left. All right, let's do another 5-minute break, and then we'll come back and we'll keep going through this, and then we're going to work on the first programming assignment together.